Hello. In this video, I will briefly go over some common techniques for finding the limit. I will introduce one-sided limits, limits at infinity, the conjugate method, and L'Hopital's rule. So we're just going to go over some common techniques. So by now, you should know a limit is nothing more than a y value as x approaches a number. That's what a limit is. It's just a y value. A limit can be a real number like 6, pi, and yes, 0. 0 is technically a real number, or negative 3.2. It could also be negative infinity or positive infinity. So what you do not want for the limit to be is in an indeterminate form. So you don't want to have that as your answer. What is an indeterminate form? It's any of these. So 0 over 0, positive infinity over infinity, positive plus or minus infinity over plus or minus infinity, infinity minus infinity, 0 times infinity, 0 raised to 0, 1 raised to infinity, or infinity raised to 0. Those are all in determinate form. Okay, so you don't want to have that. So what you can do is there's some techniques you can do so you won't get those in an indeterminate value for your limit. So let's go over it quickly. Let's briefly go over some of the techniques you can do to not get an indeterminate value. So first step, what I would always do is try plugging the x value into the limit problem. Sometimes it's so simple that you just have to plug it in and you'll get a real number. Okay, so that's what I would do first. If that doesn't work, what you can do, so if your limit problem is in the form of a rational form, meaning in a fraction, try factoring out and maybe something will cancel. Then once you have it in the most simplified form, or yeah, plug your x value into the newer equation. That can work. Okay, so try factoring out. If something cancels, cancel it and then plug in the x value into the newer equation. Okay, so if that doesn't work, if your limit problem is a rational function, try multiplying both sides by the conjugate of the numerator and denominator. So yeah, sometimes you can get away with it by multiplying top and bottom by the conjugate of the numerator and denominator, and I'll explain. 4. Then what if you're dealing with one-side limits? So one-side limit is when your x value has that plus sign or minus. So if you see that plus or minus, it just means, so for example, limit as x approaches 5 and then you have a positive. That positive sign just means it's 5 to the right. If it was 5 to the minus, this does not mean negative 5. It means 5 to the left. So what I would do is try plugging in x value larger or smaller of the x value given. If possible, try graphing the function. So you can graph the function, if that helps. You can plug in a value and you'll see that it's either infinity or negative infinity, or the horizontal asymptote. So we'll talk about that more when we do an example. When dealing with rational function, so this is like dealing with infinity when your x value approaches infinity. So when you're dealing with a rational function, divide each term by the highest term of the denominator. Remember, the limit of a rational function is always the horizontal asymptote. And I will do an example to show you. Okay. And rule 6, if all steps fails, what you can do is apply L'Hopital's rule. That's basic L'Hopital. It's like the last resort. It's something you don't want to use. But if all fails, you can try L'Hopital's rule. Basically, you rewrite the problem into a rational function. So put it in the form of f of x over g of x. And then what you want to do is take the derivative of f of x and g of x, sometimes more than once. sometimes you can just get away with it with just once. And then when you plug in your x value, you should get a real number. So I'll go over, I think I have one example of a L'Hopital's rule. Okay, so let's start with example 1. So example 1 says find the limit. So the limit as x approaches 2 of x parentheses x minus 1 times x plus 1. So this 2 does not have a plus or a minus, so it's not a one-sided limit. It's not a rational function, so we can't factor anything out. So what I would do is just do rule 1. Plug in your x value into your problem. And let's see if you have a real number. So wherever you see an x, plug in 2. So it's 2 parentheses 2 minus 1, 2 plus 1. So that would be 2. And then 2 minus 1 is positive 1. 2 plus 1 is 3. And then 2 times 1 times 3 is 6. Okay. I get a real value, so that works. So this was a simple one because all I had to do is plug in your x value into the limit problem and you get a real number. Okay, so that was example 1. Simple, right? But unfortunately, they're not always that simple. They get more complex as we move on. So let's move on to example 2. So find the limit. The limit as x approaches negative 3 of this rational function x squared minus 9 over x plus 3. So what I'm going to do, like, you should always see if you could just get away with it by plugging your x value in. But I don't think that'll work because if I plug it in, right? Negative 3 squared is 9 minus 9, and then negative 3 plus 3 is 0, 0 over 0, right? So you have what's called an indeterminate form, which we don't want to have. So what can I do to make it get a real number? So, well, since it's a rational function, can we factor this? Can we factor this? Yes, you can. The x squared minus 9 is a perfect square. So I'm going to rewrite the problem as this, right? So x squared minus 9 is a perfect square. It can be factored out as x plus 3, x minus 3. And then the bottom is just x plus 3, right? So what do you see that cancels? The x plus 3 cancels. So you're left with the limit as x approaches negative 3 of x minus 3, okay? Now, let's see if it works now. Now let's plug in our x value into the newer one, this one. So it would be negative 3 minus 3, which is negative 6. Look, negative 6 is a real number, so it works. So this is our final answer, negative 6. Okay, so this one I had to just factor and cancel, and then I plug in the x value. Okay, let's move on to example 3. Find the limit as x approaches 3 of square root of x plus 1 minus 2 over x minus 3. If I plug it in, so if I just plug it in immediately, the bottom will not work because if you plug in x for 3, it would be 3 minus 3. And I already know that the 0, anything 0 on the bottom is undefined, right? So plugging in will not work. What can I do? Since it is a rational function, can I factor it? Can I factor anything? No, I cannot. What I would have to do is, the clue is there was a minus in the middle. You'll get more advanced, but I know that I have to multiply top and bottom by the conjugate. And this time I'm going to multiply top and bottom by the conjugate of the numerator. There's really no trick, you just have to know it. But as you do more limit problems, you'll see that you would have to multiply top and bottom by the conjugate of the numerator. So what is the conjugate of the numerator? It's basically the same thing, just opposite sign. So it's going to be square root of x plus 1 plus 2. and do it top and bottom. Okay. So on the numerator, what is square root of x plus 1 minus 2 times square root of x plus 1 plus 2? What's so special about that? It's a perfect square. So you could FOIL it out one by one, but I don't want to do that. So I'm just going to do the shortcut. So you can rewrite this as, I'm going to use the perfect square rule. So it can be expressed as x plus 1 square minus 2 square. Okay. And then on the bottom, I'm just going to do not FOIL it out. Just leave the bottom alone for right now. And you'll see, just leave it out. Just write it out. Okay. So on the top, square root of x plus 1 squared, that is when you square a radical, the radical disappears. Minus 2 squared is 4. And if you simplify that, that would be 1 minus 4 is -3. Okay. And then on the bottom, you're just left with x minus 3 times square root of x plus 1 plus 2. And you'll see why I left that at bottom, because now what do you see that cancels? The x minus 3 cancels. So you can rewrite your problem as the limit as x approaches +3 of our newer equation. So your newer equation, x minus 3 cancel, you're left with 1 over square root of x plus 1 plus 2. Okay, now go ahead and plug in your x value into your new function. So it's going to be 3 plus 1 plus 2. So that's 1 over 3 plus 1 is square root of 4 plus 2. Square root of 4 is 2 plus 2. Bingo. What's 1 plus 2? So it's 1 over 2 plus 2 is 4. This is a real number, so it works. Okay, so this one works. So this one, I had to multiply top and bottom by the conjugate of the numerator. Okay. Okay, let's move on to example 4. So this one says find the limit as x approaches 3 plus. So this is called a one-sided limit. They get more complex as we move on. You will have to learn about the continuity test. But right now, I don't want to go over that. I want to just show you that when you're dealing with one-sided limit, for example, x approaches 3 to the right, because it's a plus, what you want to do is you can either draw the picture. This is a rational function. Or what you could do is plug in an x value. So it's 3 to the right. So what you could do is plug in an x value slightly larger than 3. I wouldn't use 4. I would do something slightly larger than 3. So maybe like 3.2. So if I put 3.2, it would be 3.2 minus 3. And then 3.2 minus 3 is 0.2. And then if you put 1 over 0.2, it comes out as 5. Okay, so if your number is positive, it's going to be, if your number is like a positive number, it's going to be, your final answer will be positive infinity, right? If it's like a negative, it would be negative infinity. And then here, so your final answer is positive infinity, not 5. And I'll show you. So let's graph it. Let's graph this function. Y equals 1 over x minus 3, right? What kind of graph is this? This is a rational function, right? And how do we graph a rational function? We need a few things. We need the vertical asymptote and the horizontal. Okay, so let's find the vertical. So to find the vertical, you simply set the denominator to 0 and solve for x. So we're going to add 3 and 3. And then let's find the horizontal. So the horizontal, this is technically bottom heavy, right? When the degree, when the degree, so the highest, so it's going to be y equals the highest term on the numerator is 1. The highest term on the bottom is x1. So when the degrees on the bottom is bigger than the top, it's bottom heavy, so your horizontal asymptote is 0. Okay. You could also put this in Desmo if you don't, if you're like, you don't want to graph this by hand, but like let's say you have an exam and your teacher can't, you're not allowed to use graphing calculators. You can graph it by hand. So here's the x value 3. Do a vertical dash line. Okay, and then our horizontal asymptote is y equals 0. Let's use, what color should we use? Ooh, let's use gold. So y equals 0 is the golden dash line. Now, what you need to do is plug in some x value. So let's plug in the x value 4. You plug in 4 into the function, get 1 over 4 minus 3, which is 1 over 1. You have a coordinate at 4, 1. That. And that's good enough because you know it's not going to go below the golden dash line and it's not going to pass the green dash line. Or what is it? What is this one called? It is called the ocean dash line. Okay, so it's going to look like this. Now let's do the other side of 3. So if I plug in the x value 2, we have 1 over 2 minus 3, which is 2 minus 3 is -1. So you have a point at 2, -1. Here's 2, -1. Okay, so here's your point. Here, you know it's good. That's good enough because you know it's not going to pass. It's not going to pass the golden dash line, and it's not going to pass the green dash line. So it would look something like this. Okay, now you tell me, what is the y value as x approaches 3 to the right? So here's 3, right? If you look at to the right of slightly to the right of it, the y value shoots up to positive infinity. So that is why our answer is positive infinity. What would be the limit as x approaches 3 to the left? So here's 3. If you look slightly to the left, the y value shoots down to -infinity. So this problem, we'll go more in depth with limits. This is called one-sided limits, but I just want to say that the limit as x approaches just regular 3 will be d does not exist because the limit as x the limit as x approaches 3 to the right must equal to the limit as x approaches 3 to the left. So the limit as x approaches 3, it will technically does not exist because the limit as x approaches 3 to the right must equal to the limit as x approaches 3 to the left. If they do not, or if they're not the same, the limit of 3 does not exist. So they're not the same. But the question only asks, what is the limit as x approaches 3 to the right? It's positive infinity. Okay, so what you could do is graph it, or you can plug in an x value slightly larger than 3. Okay, so this is called a one-sided limit. This is example 4. Okay, let's move on to example 5. Okay, so the limit as x approaches -infinity of the rational function 4x squared minus x all over 2x cubed minus 5. So Now, if you look at our x value, it's a little strange. Our x value says negative infinity. We're used to having like x equals like 3 or one-sided limit 3 to the right, right? We haven't learned about negative infinity, but it's okay because what kind of graph is this? This is a rational function. So what is the limit of a rational function? It's basically the horizontal asymptote. So I'm going to say that the limit is our horizontal asymptote. And what is our horizontal asymptote of this rational function? Well, what is the highest term on the numerator? It is 4x squared. What is the highest term on the denominator? It is 2x cubed. So what is the rule of a rational function when the degree on the bottom is bigger than the top? So the rule is it's bottom heavy. And when it is bottom heavy, the horizontal asymptote is 0, y equals 0. So that means our limit is 0. Okay. But unfortunately, you can't just say our limit is 0 because our horizontal asymptote is 0. You're going to have to do some work. So what you're going to do is you're going to divide each term. You're going to divide each term by the highest. You're going to divide each term by the highest power of the denominator. So if you look in our bottom, our highest term is x cubed, right? So what you're going to do is divide each term by x cubed. So it would be 4x squared over x cubed minus x over x cubed. And then on the bottom, it's 2x cubed over x cubed minus 5 over x cubed. Okay, so over here, what's 4x squared over x cubed? You subtract, when you're dividing with the same base, you subtract. So it's 2 minus 3 is -1, so that would be 4 over x minus, what's x1 over x cubed? 1 minus 3 is 2, so that would be 1 over x squared. Okay. And then on the bottom, 2x cubed over x cubed, the x cubed cancels, you're just left with 2 minus 5 over x cubed. Okay. So now you can rewrite this problem as the limit as x approaches negative infinity of our newer problem. So this is our newer one. So it's going to be 4 over x minus 1 over x squared over 2 minus 5x cubed. Okay. Now we can plug in our x value. So wherever you see an x, plug in infinity. So 4 over negative infinity minus 1 over infinity squared is really just infinity. And then this 2 just stays as 2. Minus 5 over infinity cube is just 5 over, what's infinity to the third power? It's still infinity, right? And then we evaluate. So let's look at this term here. What is 4 divided by negative infinity? Well, 4 over a very small number or a very large number is just going to be 0. Or negative 0, right? Which is technically 0. Minus, what's 1 over a very large number? Positive 0, right? And then on the bottom, it's 2 minus, what's 5 over infinity or 5 over a very large number? It is 0. Okay. So on the top, what's negative 0 minus 0 is still 0. And then on the bottom, what's 2 minus 0? That's just 2. Now you tell me, is this a real number? Is 0, what is 0 divided by 2? It's technically 0, right? It's a real number, so 0 works. If it was 2 over 0, you're in trouble, right? That would be undefined or indeterminate. And you'll probably have to do some other technique. But we're okay because 0 divided by 2 is a real number, right? 0, if you have a 0 on the top, that's fine. It's just you can't have a 0 on the bottom. So your final answer will be 0, which is technically a real number. Okay, so this is limits dealing with infinities. Let's move on to example 6. What is the limit as x approaches positive infinity of this rational function square root of x squared plus 2 over 3x minus 6? Do not even plug in infinity. It will be into your x value. It will be it would be an indeterminate value. So what you want to do is, I guess, because this is a rational function, so you would divide each term by the highest term of the denominator, which I believe is just x. But before we do this, we can simplify this. We can simplify the numerator. What is the square root of x squared plus 2? Well, that's equivalent to saying x squared plus 2 raised to the 1/2, right? So remember when you raise, what's the rule for when you're raising exponents? You multiply. So x2 times 1/2 is just 1, so it's just going to be x to the power of 1. And then plus what's this 2 has a power of 1, so what's 1 times 1/2? That's 2 to the 1/2, correct? And then on the bottom it's 3x minus 6. Okay, so now what you can do is divide each term by the highest term on the bottom. So it's going to be x over x plus 2 to the 1/2. If you want, 2 to the 1/2 is the same thing, square root of 2. So you're going to divide that by x. And then on the bottom, 3x divided by x minus 6 over x. Okay, so you can rewrite this as limit as x approaches positive infinity. X over x is 1 plus square root of 2 over x over 3x over x is the x cancelers lost for 3 minus 6 over x. Okay, now you can plug in your x value infinity. So it's 1 plus square root of 2 and then replace x with infinity over 3 minus 6 over infinity, right? Okay, so this 1 stays the same. And then what's radical 2 over a very large number? We said that will be 0. And then on the bottom it's 3 minus what's 6 over a very large number? That becomes 0. So on the numerator, what's 1 plus 0? 1. And then on the bottom, 3 minus 0 is 3. Hello. 1/3 is a real number, so we're good. We don't have to use another technique. So this is our final answer. Okay. Okay, good. Now let's move on to example 7. So in example 7, this is still dealing with infinities. You plug in infinity into the problem immediately, it'll be an indeterminate value. This one's not too bad. You just divide each term. You divide each term by the highest power in the denominator. So if you look at your denominator, what is the highest power? It's just this x1, right? So you're going to divide each term by x or x1. So 2x divided by x minus 5 over x. And then on the bottom, it's 3x over x plus 7 over x. Okay. And they would be limit as x approaches positive infinity. 2x over x is just 2 minus 5 over x. And then 3x over x, that's just 3 plus 7 over x. So now you plug in your x value for infinity, so it's 2 minus 5, and then x is infinity, 3 plus 7 over infinity. Okay, so this is 2, and then minus, what's 5 over a very large number? It's 0. And then on the bottom, it's 3 plus, what's 7 over a very large number? It's also 0. Okay, so on the numerator, 2 minus 0 is 2. And then on the bottom, 3 plus 0 is 3. that works because 2/3 is technically a real number. So your final answer is 2/3. Okay, so this one wasn't too bad. Okay, let's look at our last example. Find the limit as x approaches positive infinity of x to 100 divided by ln of x. So if you try plugging this in, it will be indeterminate, right? It would be infinity over 100 and then ln of infinity. What is ln of a very large number? It would be infinity. So you would have infinity over infinity, which is indeterminate. Okay, so we can't do that. So what we're going to do is, it is technically a rational function, but this one is strange. We can't just divide each term by the highest power of the denominator. We can't factor anything out. We can't multiply top and bottom by a conjugate. So what is the last resort is L'Hopital's rule. So L'Hopital's rule is basically you just take the derivative of the numerator and then you just take the derivative of the denominator maybe once, maybe twice, until you get a real number. So let's first figure out our f of x and our g of x. So my f of x is my numerator, which is x to the 100. And then my g of x is the bottom, which is ln of x. Okay. So let's take the derivative. So f prime of x. What's the derivative of x to the 100? That is 100 x to the 99, right? You just apply power rule. And then what's g prime of x? The derivative of L of an x is 1 over x. So it would be the limit as x approaches positive infinity. And then f prime, so we're going to put that on the numerator, our f prime. Our f prime of x is 100 x to the 99 over, and then in the bottom is your g prime. So your g prime is 1 over x. Now I tried plugging in infinity into this problem, into this newer equation. But what you want to do is simplify this a bit, right? Because we have a complex fraction. So let's simplify this. So this is my numerator, and then this is my denominator. So we have a complex fraction. So what we can write it as 100 x to the 99 divided by 1 over x. And then what I can do is cross multiply. So what's 100x 99 times x? That is 100x 100, right? And then on the bottom, what's 1 times 1 is 100. So this simplifies as 100x to the 100. So now let's put it in the most simplified equation. So this is going to be 100x to the 100. And all you got to do is plug in x for infinity. So it's 100 and then infinity raised to 100. It's just 100 times, what's infinity raised to 100? It's like infinity, right? And then what's 100 times infinity? It's just infinity. And that's still part of an answers, right? We can have infinities, we can have negative infinities. So this works. So our final answer is positive infinity. Okay, so this was just a small sample of limits. I mean, of course, there's going to be other techniques and then there's other techniques and then you get more in depth, and we'll go over that later on. So this is just basically just a small intro to limits. Yeah, so I'll stop here.